Okay, so as we discussed about the course, in the course we talk about two things. One is algorithm design techniques, and another part is the data structures. And generally they go together that you need efficient data structures for efficient algorithms. So you need to learn what are the data structures and how to use them, which one to use and what kind of algorithm. Okay, so this connection you learn while you're solving problems. So for example, you learned how data structures like queues would be very helpful for solving uh, some of the problems that are to do with graphs, and they will do with various. You will use various kind of algorithms there. And similarly, we talked about binary trees, AVL trees, and all, right? And actually, after the break, we will talk about more data structures. But I think this algo design techniques part will be mostly complete before the break. So what are the techniques we covered in algo design? What are the techniques we covered?
Dynamic programming, divide and conquer.
Divide and conquer. Then we talked about dynamic programming. Okay. Now what is the similarity between the two? How are these two similar? What is similar among these techniques?
So both run on a recursion formula.
Okay.
In both, we solve the smaller
Recursion, what is the
instance.
idea of
But
recursion?
Sir, we divide the larger
we got
problem into
Yeah, the
smaller
the
formula that
subproblems.
we use for recursion are both are used in both of them, but we solve divide and conquer from top down and dynamic programming from bottom up.
Good, good. So one thing that is common is that they use solutions. Similarity is that they use solutions to the subproblems. So that means I don't want to solve my larger problem immediately. I'm saying, okay, can I break them into smaller subproblems and can I solve the subproblems first and use that to solve my larger problem? But the difference is that, yes, this is uh, top down and this is bottom up. How does it help? So how does bottom up help? Why bottom up? Why do you need a bottom up approach in dynamic programming?
So it helps to reduce some redundant terms that we calculate repeatedly in divide and conquer.
So what happens is that when you are breaking your larger problem into sub problems, right, smaller sub problems, what may happen that you may come up with the same sub problems again and again and again, right? So sub problems repeat. So that means if you want to solve it again and again and again, that is very inefficient. So in bottom-up approach, what you do, you keep on recording the values. What is the solution to this problem? Let me record that once and for all. Okay. So and you do it in a very systematic manner by you fill up a table in dynamic programming. So you have the subproblems that repeat but solve only once. On the other hand, what you will do in divide and conquer, you will keep on calling subproblems, and if the subproblems are repeating, you will have to solve them again and again because you don't store them, right? And that is where did Professor Animesh Mukherjee talked about memoization at the end? Yes, no?
No, sir.
Okay, that's fine. We'll talk maybe sometime. So yeah, so so in divide and conquer, you do go top down, but then uh, when your solution to the main problem is of very special type, your sub problems will repeat. Okay, but generally the way the problems we were doing there, they were not repeating. We were just dividing into two, again dividing into two, and so on. But if you talk about okay, Ti is max of all Ti minus j and things like that plus something So you will find problems repeat, and very simple example is the Fibonacci series, right? Fibonacci series. So okay, so I guess you understand the difference between the two. The good thing is they are similar in the sense they want to solve a larger problem using smaller subproblems, and the difference is that in dynamic programming you can keep on storing your solutions. Okay. Now, why do we need a third programming paradigm? So divide and conquer dynamic programming are there. And then as you can see from the title of this notes, I'll be talking about greedy algorithms. So then I'm saying we have a third algorithm design paradigm, that is greedy algorithms. Now, what extra we will do? What extra we will do? So it is more similar to dynamic programming than divide and conquer. Okay, so this has similar with dynamic programming, but differs in one very important way, as the name says, greedy. Okay. So what we will do in greedy algorithms is that, so in dynamic programming, we generally try to express the solution of a larger problem in terms of the optimal solution of its subproblems, right? So that's what we do. And there we have a situation something like that okay, this solution to a larger problem will be in terms of subproblems, and I will compute all of these, take a max of that or min of that, something. Generally you do that, max, min, or some similar operations you do. So while you are doing this, what you will do in greedy, instead of doing this max or min sort of operations, can you identify one property that will always be true for an optimal solution? So instead of taking this max, min, or similar other things, can you identify a greedy property that will always be true for an optimal solution? And here there's a catch: for at least some optimal solution. May not be true for all optimal solutions, but it will be true at least for some optimal solution. That means if you use that property, you are guaranteed to get. So that means there's a guarantee. That is a guarantee to achieve the optimal solution. And because you do things, instead of doing max min, you will do just greedily take that. So you save your computational time. So you get a more efficient algorithm. And you get a more efficient algorithm. Okay. How do we decide those greedy properties, and how will this guarantee come? How will we guarantee that this property ensures that this final solution will be the final output will be at least part of one optimal solution? And that is what we will learn about greedy algorithms. Okay, and yeah, those who like proofs, yeah, here we will do proofs. So that means you have to do some sort of proof. So you need to do proof. Okay, how do I prove that yes, this greedy property gives me an optimal solution? So here we will also do proofs. Okay. So actually you will see in greedy algorithms, in terms of coding, there is not much. Code will be very easy, right? A bit of relief, right, in dynamic and greedy. So bit of relief in coding. So there's not much about coding. It's more about thinking about that property and proving that this is optimal. Okay, that is what we will see. So let me start with a very simple problem. Okay, and because you are now tuned to thinking in terms of dynamic programming, let's try to solve it using dynamic programming, and then we will see where we can make a change to go from dynamic to greedy. So what is my problem? It's a simple problem that you have to encounter every day, maybe. So we call that a coin change problem. What is a coin change problem? Suppose, and yeah, so whenever you feel I'm going fast, somebody has to stop me. Okay, I'm trying to go slower, but if anybody feels I'm going faster, please stop. Okay. So suppose you have to make a change of n rupees. And for that, you have to use some coins. So suppose you have to give some shopkeeper 46 rupees or something. And you can do that using various notes. And suppose here you only have coins. And you have various coins. So using coins of denominations. So here, suppose you have 1, 2, and 5 rupee coin. And assume you have sufficient number. So you have sufficient number of each coins. Right, what is the problem? I can just give all 1 rupee note, right? All n 1 rupee note. So what is the problem here? Is that even a problem? I can give all 1 rupee coins.
So we need to find the minimum number of
So we need to
denominations.
define some criteria, right? What is my optimization criteria? Right? In dynamic programming, we learn about, okay, I have an optimization criteria that I need to take care of. So here, what is the optimization criteria? That is, okay, you need to use minimum number of coins. So then I cannot just use 1 rupee coin because then I will need all n coins, right? So I can possibly do better than that. So that is my optimization criteria. Now let's think in terms of dynamic programming. How you will solve it in dynamic programming. Okay, what are the things? You need to define what are your subproblems. How do you write the solution of your problem in terms of smaller subproblems, the recurrence formula. Okay, so in dynamic programming, how will you define your subproblems here? What is a good subproblem definition?
dp of I is the number of minimum coins to achieve I rupees.
Good. So let me call it change. Change of I is the minimum number of coins required to make a change for I rupees. Okay, so then you know what is your final answer? So your final answer, what is your final answer? In terms of
Change
subproblem, change of n.
Change of n.
So yes, I defined my subproblem. Good. So I'll change I from, let's say, 0 or whatever up to 1. Now, next thing is, I need to understand what is the optimal substructure. What is the optimal substructure? So suppose I need to make a change for I rupees. What can I do? And suppose this is large.
So we will see I minus 1, I minus 2, I minus 5.
I can say, okay, I have three
Whichever is less.
possibilities. I can use 1 rupee coin. So then I remaining problem is I minus 1. I can use 2 rupee coin. Remaining problem is I minus 2. I can use a 5 rupee coin. And remaining problem is I minus 5. That's what we do. Yes. And then I can see, okay, so what is the optimal solution? So how can I change I, minimum number of coins required to make a change of I rupees? How can I write in terms of my subproblems?
1 plus minimum of
I need
change.
1 coin in all 3 cases, 1 coin, 1 rupee, 2 rupee, 5 rupee, plus I will take a
Minimum
minimum
of
of the two.
change I minus 1.
Yes, very good. Minimum of change I minus 1, change I minus 2, change I minus 5. Okay, that is your recursion, that is your recursive structure. And then you have to define your base cases here. So because you are using I minus 5, so you have to define base cases up to either 0 to 4 or 1 to 5, whatever. So let's say I define for base case. So what is my change of, let's say 1 to 5. Change of 1, what is the value? Change of 2. Yes, change of 1.
1.
Change of 1.
Change of 2 is also 1. I will use a 1 rupee
Yes.
coin. 2, 1. I will use a 2 rupee coin.
3, 2.
2, 1 and 2. 4,
2.
2.
and 2. And 5 is 1. It's 5 rupee coin. So base cases are done. And then I can write a simple dynamic programming algorithm for solving this. Good. And what is the complexity?
Order n.
O
Order
of
n.
n.
O of n. Only that every time I'll have to take a minimum of these three things. I'll have to they already computed anyway. So I'll have to take a minimum of these three things and then I'll compute this value. So actual computations will be roughly like 3 times n plus something. Okay. So this is your dynamic programming, right? All of you are very much conversant with this. Now, where do we need greedy? Now, why do I need a greedy algorithm here? What will I do with greedy now?
So we will give as many 5s and then we'll see for the last part.
Remember what I was saying? So whenever you write your solution in terms of subproblems, you can see, okay, there is one property that will always be true for an optimal solution. So can I identify one property that is always true for an optimal solution? That instead of actually computing these three things, finding min, can I think of one property that will avoid doing this minimum?
So give maximum number of 5s and then see what is remaining.
Yeah.
1,
So
2,
what
3,
will
4.
be a greedy property? The greedy property. So I have to find out what is the greedy property. Greedy property is, yes. If I can
Sir-
choose a greedy coin, yes, tell me.
Sir, n modulo 5 will be the means the total of 1 and 2, and the remainder modular 2 will be the number of ones.
Good, good, good. So yeah. So greedy properties. If I can choose a coin of larger denomination, I should choose that. So that is, so greedy will be if n is greater than or equal to 5, select 5.
But sir, this will work only for this set of denominations, right? Like every time if we take maximum.
Where I have told you that this will work for all denominations, have I?
Okay.
I am working for a specific case, right? 1, 2, and 5. Else if n is greater than or equal to 2, you select 2, and else select 1. It's as simple as that. That is your greedy algorithm. So that means you can accordingly write your pseudocode also. So I don't know whether you want me to write, but change n. Here you will see, okay.
Sir?
Yes.
Sir, so if the coins were 5, 3, and 2, would you have used the same method?
Yeah, I'm coming to that. Firstly, let me talk about this particular problem, right? Then I'll
Okay.
talk about the other cases. Okay. So you can define base cases, and I think you can write. I don't need to write this program. So you can write. I think you can write this program. That is very easy. So So then what am I doing? So if there are actually, if I have to make a change for n rupees, I'm choosing n by 5 floor, that many 5 rupee coins. And then I'll see what is remaining, and accordingly, whatever I can choose 2 rupee coin, I'll do that. And then whatever remaining, I'll choose 1 rupee coin. That's all I will do. So in that way, yeah, you don't even need an order algorithm. You can use actually a constant time algorithm. So you can actually use a order one algorithm for telling what is the minimum number of coins. So yeah, so now yeah, looks very easy. But then what was the other thing I said? I said, okay, first thing is identify a greedy property. And then you have to prove that this will give you an optimal solution. So how will I now, so suppose now I have taken this greedy property and we sort of agree, like, I don't know if anybody feels this will not give me an optimal solution, but we sort of agree that this will give me an optimal solution. Now the next question is, fine, we agree, but can we prove that? Can we prove that this will give me an optimal solution? So how would the proof work? How will I go about proving this?
Sir,
Sir,
in
we
this
can
case, suppose we don't have the maximum number of 5, then we have a less number of 5, then we can add 2 and 1 to get a 5.
Okay.
And it will make the coins less.
So, okay,
Quite
so this one is very important. This one is very important. Please understand. So how do you do proofs in greedy algorithm? So the trick is that, fine, you have a greedy approach that will give you a solution. Right? So you think of your greedy solution. There's a greedy solution. You can call it G. So to prove that this is optimal, assume there is an optimal solution. So assume there is an optimal solution O that is not same as G. Okay? That is not the same as G. So that means it differs from G at least in some way. It's not the same as. So assume there is an optimal solution, okay, and then you prove that, and starting from here, construct another optimal solution O prime that is same as G. So start from O, that is an optimal solution name, not same as greedy, and then you say, okay, it differs from greedy in some way, let me do some modifications so that it still remains optimal, and while doing that, you take it to the same solution as greedy, and that's how you prove it. Okay. So you say, okay, it's an optimal, not same as greedy, let me say make some modification so that it will still remain optimal, and only make modification that will not change its optimality. Its optimality should continue to hold, and then you say, okay, now we have found that, yeah, another optimal solution O prime, and that is same as my greedy solution. So generally, yeah, this is one of the nice ways of proving optimality for a greedy solution. So let's see, I'll just give you a quick hint for this, what we will do. Okay, so you have a greedy solution, right? So
sir, what is the meaning of this? Starting from here, construct another optimal solution.
Right. Okay. Yeah, I'll tell you that. What does it mean? So see, in this case, your greedy solution will be like three integers. How many coins you took for 5 rupee, right? 3, 5. How many coins you took for 2 rupee? How many coins you took for 1 rupee, right?
Yes, sir.
An optimal solution will be something like, yeah, I could have written G5, G2, but something like 05, 02, 01. How many coins you took for 5 rupee, 2 rupee, 1 rupee, an optimal solution. So G1. So what I was saying, so if O is same as G, you are done. Nothing to be proven, right? But in general case, you can say, okay, let's assume that O is not same as G. So let's assume O is not same as G. That means it will differ from G at least in one of the 3 points. O differs from G at least in 1 point. Okay.
So at least 2 points.
See, at least 1 point is, I mean, a generic thing. Maybe in this particular case, it will differ in 2 points. Okay. It will differ in 2 points. Yes, I agree. But I'm just saying, in general, at least 1 point. Yeah, that anyway is superset of at least 2 points.
Okay.
So differs at least in 1 point. Okay. So then we can say, okay, let's say, okay. So let's say, assume O5 is not same as T5. So let's say assume that O5 is not same as T5. That means what are the possibilities? So can O5 be larger than T5?
No, sir.
Can O5 be larger than T5?
No, sir.
Why not?
Because we are taking maximum
Because
number of
the
5.
greedy property says that I will take as much 5 rupee coin as I can. I cannot take even a single 5 rupee coin more, right? Because of the greedy property. So that means O5 has to be smaller than T5. Right? O5 has to be smaller than T5. Now the question is that possible in an optimal solution? So O5 is less than T5. That means what? So optimal solution is using at least one, or let me just write, is using 1 2 rupee coins to make change for at least 5 rupees, right? So at least for 5 rupees, optimal solution is using 1 or 2 rupee coins. Can I say that?
Yes, sir.
Right. So then what are the possibilities? See, I'm not doing a full thing. I'm just giving you a hint. I'll do a full thing in the next problem. So what are the possibilities? How can it make change for something more than 5 rupees using 1 and 2 rupee coins? It can use 3 2 rupee coins if it had more than 5 rupees, right? Or it can use 2 2 rupee coins and 1 rupee coin. Or it can use 2 rupee, 1 rupee, 1 rupee, 1 rupee. Or it can use 1 1 1 1 1. It has to use at least one of this. It will have to use at least one of this. One of this needs to be used in O. Anybody disagrees with that? Okay. I need to use at least one of this. Sorry, there is one more thing. So then what you show in all of these cases, you show that in all these cases, you can actually do something better. You can actually do something better. So if it was using 3 2 rupee coins, how can you do better? What can you do to do
5
better?
and 1.
5 rupee and 1 rupee coin. If it is using 2 to 1, use a 5 rupee coin, 5 rupee coin, 5 rupee coin. So in all these cases, you can do something better. So that means, what does it imply? So this was exhaustive. All the possible cases we considered, and in all the cases, I can do better. I can use less number of coins than the optimal solution. That means what? What does it imply?
It contradicts the optimality of O.
Yeah, so at least it says that O5 should be same as T5. O5 and T5 should be same, right? They need to be same, they cannot be different, O5 and T5. So we started assuming there's an optimal solution different from greedy, and then we said, okay, let's assume O5 is say not same as T5, and then we came to conclusion that O5 has to be same as T5. Okay, so then okay, O5 is same as T5, done. Then you try with O2, you will come with the same conclusion. You will come with the same conclusion, and yeah, and that's how you will show. In this case, you will directly show that O has to be same as G. O itself has to be same as G. Is that okay, or you want me to explain this part more? I can do that.
Sir, in the cases considered, why are we taking 3 2s?
Right, because they were at least 5 rupees, right? They can be 6 rupees, 7 rupees, 8 rupees. So this is a possibility. Suppose the remaining was 8 rupees. So you have to use 4 2 rupee coins. So that means that 5 plus was changed using 3 2 rupee coins.
But sir, here we are considering only the 5 rupee coins.
No. We are saying that in optimal solution, if it uses one less 5 rupee coin, that means it will have to use at least one of these cases. That was what I was saying. So it is using 1 5 rupee less, at least 5 rupee, could be like 6 rupee, 8 rupee, 9 rupee, 14 rupee, whatever. So there it has to use at least one set of this. So suppose 14 rupees were remaining, so then it can use 7 2 rupee coins, right? So then none of these cases will cover that. This case will cover that.
Yes, sir. Okay. Thank you.
So that is why I was saying this is the exhaustive thing that
Sir?
one of this set. Yes.
Sir, but we are assuming only O5 and T5 differ. So the difference in the number of coins, like, means what we have to cover up should be a multiple of 5 only, sir, because we are assuming that O5 and T5 differ.
No. The proof is not complete. I started by assuming. See, we said that they are different. Let's assume they are differing at the first place itself. O5 not same as T5, and then we came up and we showed that O5 and T5 have to be the same. That's what we have done. Now next, what you will start assuming, let's say O2 and is not same as T2. Okay, so till now what we have proven, so now we know that O5 is same as T5. But what about O2? O2 can be, let's assume O2 is not same as T2. Let's assume O2 is not equal to T2. Then what are the possibilities? How many rupees of change we need to consider now? Maximum how many rupees?
4.
4.
4 rupees, right? Because O5 T5 was same, that means we are left with at most 4 rupees. And in this case, what you can do, simple thing is there are only 4 rupees. So let's take 1, 2, 3, 4. Consider all the cases, right? When there was only 1 rupee, anyway, both of them have to be 0, right? If there was 2 rupee, the only possibility is that T2 was 1. T2 has to be 1, a greedy choice. O2 can be 0. Yes, that is the only possibility. In that case, what you will say? That means it has to use two 1 rupee coin to make the change, but I can do better. In greedy, I'm just using T2 is 1 and T3 is 0. And here O2 is 0, O3 is 2. Right? Not an optimal solution. If there were 3 rupee, what was the T2 is 1, T3 is 1. And the only way it can be different, O2 is equal to 0 and O3 is equal to 1. Again, sorry, 3. Again, this is not optimal. Here I am using 2 coins, here I am using 3 coins. In case of 4, T2 will be 2 and T3 will be 0. And what are the 2 ways it can be different? One is O2 is 0, O3 is 4. Second is O2 is 1, O3 is 2. Right? In both the cases, greedy gives me a better solution. So again, they are not optimal. So again, exhaustively, you can see that in all the cases, greedy gives me a better solution. That means my original claim was wrong, that O3, the optimal solution is different from greedy. So that means now O2 should be same as T2 and O3 should be same as T3. And, oh sorry, why I'm writing O3? I'm sorry, there should be O1, right? T1 and the way I defined it. So please read that. Okay, do not confuse with that. So we have now proven O5 is same as T5, O2 is same as T2, and O1 is same as T1. That means O is same as G. So here we have directly shown that my O is not optimal if it is different from greedy. This has to be same as greedy. Now tell me, does that answer your question? Swaroop, I think you have this question. Does that answer?
Yes, sir.
Okay. Anyone has a question right now? I'll pause. Anybody has a question? Something
Yes,
that
sir.
is
Means for 5 rupees, why did we cover 6 rupees? I still could not understand that. Means if they are different, then how will that include 6 rupee coins? And why only 6? Why did we not we consider 7, 8?
No, I didn't say I'm stopping at 6. Okay. So there were 3 things: O5, O2, O1, and G5, G2, G1. We said O5 has to be less than G5 if they differ at the first place, right? Now if O5 has less than G5, now you give me the answer. How many rupees O will make change using 1 and 2 rupee coins? How many rupees O will make a change using 1 and 2 rupee coins?
Greater than equal to 5.
Greater than equal to 5. Okay, greater than equal to 5. It can be any number. I'm not saying O5 is G5 minus 1. It can be any number, but it has to be larger than or greater than equal to 5. Okay. Now I'm saying for making that change, it has to use some minimum 1, 2 rupee coins. Okay. So use some minimum 1, 2 rupee coins. And I was writing down all the possibilities. Okay. So now you see in that perspective, you see. It has to either make a complete change of 5 rupee using 1 and 2, for which these 3 cases are there. There is no other case, and that I think you agree. You have no problem with that, right?
Yes, sir.
Right. But there is another possibility. Suppose it had to make change of such that it only uses 2 rupee coin. Whatever remaining amount, it only uses 2 rupee coins. Then none of these will cover that.
Oh, like that means only using 2 and 1 rupee. What cases can
you can see? I want to cover all the possible cases for accounting that 5. Yes, 5 plus. So one possibility could be it could only use 2 rupee coins for whatever remaining. So then I will say, okay, it will at least use 2 rupee coins somewhere, right? And that's what I was saying. That part I can replace with a 5 rupee and 1 rupee coin. That was all. Okay.
Yes, understood. Thank you.
Any other question? Good. Right. So simple problem. Now coming to many questions that you were asking. Oh, what if we choose nodes of arbitrary denominations, right? Okay, that is beyond this course, but I'll just give you an example. So what if we use nodes of arbitrary denominations? Will my approach always work? Will my greedy approach always work? Okay, let me take an example. So suppose your coins are 1, 4, and 5. So you have to same problem. You have to make change of n rupee using coins of 1, 4, and 5. Now question is, can I use my greedy approach?
No, sir.
That
No,
take
sir.
as much 5, then take as much 4, then take as much 1. Will that work?
No, no.
Now that's why you
No.
learn the second important thing about greedy algorithm. One thing is, if your greedy approach works, you should be able to prove optimality, right? And second important thing about greedy is, if your greedy approach is not correct, you should be able to find a counterexample. What do you mean a counterexample? Where the greedy solution is not optimal.
Sir, 8 rupees.
That means where the greedy solution is not optimal. Now, you have to understand that very carefully, right? Suppose for this problem, I say, okay, suppose your n is 6. Suppose your n is 6. Will your greedy approach give you an optimal solution?
Yes,
Greedy will
sir.
tell you
Yes,
5
sir.
and
Yes, sir.
coins. It will give you an optimal solution. But what I mean is that there is at least some n for which it will not give you an optimal solution, right? And that is a counterexample. So what is the n for which it will not give you an optimal solution? 8. This is a counterexample that you are giving. For n is equal to 8, the greedy solution will not give me optimal. So what is my greedy solution?
5, then
5, 1, 1, 1.
5, no 0, and 3 ones, right? So that means 4 coins. Anybody, can you think of a better solution? What is
Four,
the optimal solution?
2 4s.
Sir, shouldn't be 103?
Oh, I'm sorry. Yeah. Should be 103. So there are 4 coins. The optimal solution is 0 to 0. That is no 5 rupee coin, 2 4 rupee coin, and 0 to 1 rupee coin. So there are only 2 coins. So that means this is a counterexample. Very clearly should understand that here we had a greedy approach, but it is not giving me an optimal solution. So this is a counterexample. Okay. So that means same problem, if I choose different denominations, that may not give me an optimal solution. But for the 1 to 5, it was giving me optimal solution, and I proved that. Okay, so that is why proof is very important. I can't just say, oh, I think this is a good greedy solution. No, you have to prove that. Or if you think, no, I don't think this is a good greedy solution, you have to find a counterexample. Okay, and that are the 2 things you have to remember about greedy algorithm. Nothing else is much more important.
So one thing in this 541, we can say like after 20 rupees, for the like first 20 rupees, we do this normal thing where we do with DP, and then after that we use DP. Sorry, greedy. Like we'll see like by 20 rupees we use all the 5 rupee coins, and for the last part we use this.
Sure, you can try that. So right now we are only saying whether you can apply greedy or not. Okay, you may think of good solutions, but okay, now.
Sir,
he reminded
about
me of
20
something.
also I got a counter example.
I'm sorry.
28.
I'm sorry. I'm just completing the part. So he talked about combining greedy and DP. Do not worry about it. Not in the syllabus. You can do it on your own. Yes. But one thing he said, because the greedy is not applicable, the DP will always be applicable. Okay. So you can always apply DP. You can always apply dynamic programming. So that is 1 plus min change of I minus 5, change of I minus 4, change of I minus 1. This will always give you the optimal solution, because this is the optimal substructure of the problem. Okay, so this will always work, but the greedy choice which we have chosen will not. Okay, so this was the simple coin change problem. We found a problem for which greedy approach works, another problem for which greedy approach does not work. Now let's move to something that is more like a standard problem generally we start with for greedy, and that is called activity selection problem. Okay, what is the activity selection problem? So yeah, I know you have not seen the classrooms here, but think about any classrooms you have seen in your class 11 or wherever. So here I'll just take a name of a classroom that I used to take class a lot, NR121. Okay, now in the complex. So suppose you have a classroom, right? And assume assume that you have a single classroom. There's a single classroom. Okay, and assume that there are so many teachers teaching different subjects, and they want to take their classes in that classroom. So we call them. Suppose there are n requests for that classroom. There may be clubs, there may be that are organizing something, there may be some PPTs going on and so on. There's so many requests for that same classroom. Right? So each request, how can you characterize each request? For request I, how will you characterize if you have to give a request for that room? What do you need to specify? Just think of common sense. I want to request for a room. What do you need to classify or specify?
Timing.
Let's say I'm saying, okay, I want to take a class for algorithm from 10 to 11 for algo. That's a request. Okay. Now someone else says, okay, do you have signals and systems this semester?
Yes, sir.
Right. So let's say you have another request for signals and systems from 10:30 to 12. Signals and systems. Okay. Now there may be a request for, say, from 11 to 12:30 for something like a discrete. And there may be other request. Oh, I want to have a some 12:10 to 12:30. There's a club event. Okay. Club event. And so on. So different people can get their requests. Okay, I want this room for this time to this time and so on. So what they need to specify? They need to specify what is the start time of the activity, what is the finish time of the activity, right? And there's a single room. Now, what kind of, so all these requests suppose came to you, there are total n requests. Each request gave you the start time, the finish time. Now, you need to think of an optimization problem. Like what is something you want to optimize? What is your optimization problem? So you can define multiple types of optimization problem. Let me define one, that is allow as many activities as possible right? So can I allow all four? Can I allow all four activities here?
No, sir.
No, sir.
No, sir.
So that is as many activities as possible. So you can have only one activity at a given time. Only one activity at a given time, given point of time. Right? and the activity should be completed, not that, oh fine, let's just run algo for half an hour, then you give it for synthesis systems for half an hour, then you give it for discrete, and then 12th and you give it to the club. No. So you want 1 hour, you want to get a full 1 hour. That means one activity at a given point of time and should be completed. That is the criteria. Okay. So I want to allow as many activities as possible, but at a given time I can do only one activity, and that activity should be completed, and time are fixed. That means I cannot say, oh, let's move algorithm by 1 hour. No, the timings are fixed. They should run only in the given time. Now, given this optimization problem, what is the solution you see? What are the solutions? What is the optimal solution?
2.
2, right? I can
Yes.
run activities. Which one do you like?
Like algo and discrete or algo and club.
Right, yeah. So I can choose, yeah, I can choose algo and club. I can choose algo and discrete. I can choose single systems and club.
System and club.
I won't ask which one you will choose, but yeah. So you can choose at most 2. Right? You can choose at most 2. Right. So 2 is the optimal solution. Now, so this is your optimization problem. Now immediately now you can think of how will I write an algorithm. Okay. So I will proceed by thinking we are solving it by dynamic programming, and then we will see how to solve it efficiently. So I have n requests. Each comes with a start time, finish time, and SI has to be less than FI, should run at least for some time. So it should not be like a 0 time activity. So yeah, right. And there is another thing we can define. So 2 requests. So I and J are said to be compatible. Compatible means I can allow both I and J in the same solution. Okay. So both I and J may be allowed in the same solution. Can someone give me a condition for that?
Fj less than equal to Si or Sj greater than equal to Si?
Sj
greater than or equal to Fi.
Fi or
F
Si greater than
Fj.
equal to Fj.
Yes.
That means one of them has to finish before the other start. Si, Sj, oh sorry, Si and Fi. So J should be either 2 possibilities. Either I should have like this, Sj, Fj is less than Si, or I should have something like that. Sj, Fj. So this is Sj greater than Fi, and this is Si greater than equal to Fj. So that's when they will be compatible. So that means my optimization problem now I can write select a compatible subset of requests that is of maximum size. The subset should be of maximum size. Okay, that is my problem. Do you agree? This is my optimization problem.
Yes, sir.
Now, what is a even before DP, even before divide and conquer, we talked about one approach. Anybody remembers? Even before algorithms, there was an approach.
Brute force.
Brute force.
The brute force approach. Brute force. What is your brute force approach?
Try every possible way.
Yes.
Brute force means try everything possible and see which one is the best.
Try everything possible. So what do you mean by everything possible? What will you do?
All
there?
together in subsets.
Yeah.
So all possible subsets, right? And for each subset, whether they are compatible or not. And if they are compatible, I mean, just find out which of them gives you the maximum size. And select what are the compatibles, and from there select the maximum size. So select maximum size. Or if you want to do a slightly nicer brute force, what you can do, okay, I'll choose all the activities if they're compatible or not. Then I'll choose all possible subsets of n-1 size. If I find a compatible, that is the solution. Then I'll do n-2 and so on. Complexity wise, they are same. They will not, they will give you exponential time. Okay, I don't want to do brute force. No. But yeah, it tells me, yes, I can solve it. Yes, if I have infinite time, infinite resources, I can solve it. Now, then how will I think in terms of TP? It's what I think we should start tomorrow. It's already 10. So we will think in terms of DP, how I will solve using DP. Any question before we end?
Sir, in case the greedy solution is one of the optimal solutions, how will we go about proving it?
Yeah, we will do that in this case. So in the previous problem, this had to be same as optimal. There were no two optimal solutions. In this case, there can be multiple optimal solutions, right? Here we have, as we said, there were 3 possible solutions, and my greedy will be only one of those. So how will we prove it? That's what we will see tomorrow. Is that okay?
Yes, sir.
Good question. Anything else? Okay, so we will meet tomorrow 11. I'll do a 1 hour class, then we have a 1 hour tutorial about greedy. Okay, see you tomorrow. We are not seeing in lab, right?